As Claudia said, my name is Ankur Desai. You can call me Ankur. I am a professor, and I'm also department chair of atmospheric oceanic sciences at the University of Wisconsin-Madison, which is in the middle of North America, close to the large US city of Chicago. And it is winter here slowly, although the snow has not quite started to really fall, which is kind of disappointing everyone around here, but hopefully it will be soon. And I apologize for any short interruptions. It is still morning here, and my youngest daughter is still getting ready for school, so I might have to yell at her from across the hall. But so yeah, thanks for talking. I'm really excited. I know this is a very diverse audience, and so I know you may have been talking about a lot of different topics, which is really exciting. And I hope maybe down the road to participate in some of the other seminars as a participant. I'm going to go and talk a little bit more about something pretty technical, but maybe important for understanding how we can truly understand how we can monitor and understand and verify greenhouse gas emissions from urban systems. And I know you already heard a little bit about this from Ken Davis, and a little bit of a funny side story. Ken Davis was my PhD advisor many years ago now. So we do have some similar ways of thinking about the world. But hopefully these two talks can be complementary in some and give you a good idea of where we can go. So this is a picture of one of the tower sites I work at. This is a 400-meter tall television and radio station tower that we have instrumented with colleagues at NOAA and elsewhere for greenhouse gas monitoring, as well as eddy covariance. And one of my goals today is to really try to convince you that the combination of both atmospheric and ecosystem measurements co-located can really provide you a lot more information than either one of those alone. And that I encourage you, as you think about your design and your instrumentation and measurements that you're planning to make with the ICOS Cities pilot project, to consider how you might better use that information to really understand complex and heterogeneous systems. So if you are the impatient type and just want to know the main message of this talk, and then maybe go do your email on your other monitor or whatever, I will then tell you the main story here, and then you can decide which ones you might want to listen to. So to start, I will say that I don't actually work in urban systems. And so many of you are probably much more experts in some of those pieces. And so I'm happy to kind of follow up in a discussion on how we can think about how the work I'm doing connects to the work that you're interested in doing. But I have operated tall tower eddy covariance and atmospheric observations for a long time, nearly 2 decades. I run 5 of the core AmeriFlux program, FluxNet eddy covariance sites, several of which have been running for 1 to 2 decades. I operate 6 other eddy covariance across the United States. And I've also been involved in providing science advice to ICOS. I'm the co-chair of the Science Advisory Board, and so I'm pretty excited about the work that's going on in ICOS, and of course want to see this project succeed and be a useful and appropriate use of resources for the types of goals and mission that ICOS has for greenhouse gas understanding and monitoring across the continent. So as I mentioned earlier, one of my other themes is this idea of co-location of boundary layer, atmospheric mole fraction, and ecosystem flux measurements, and I'll try to explain what all of those are if those are unfamiliar concepts to you. Affords some opportunity for robust estimation of greenhouse gas sources and sinks. But one of the big challenges is that landscape heterogeneity is challenging for traditional ways that we use eddy covariance flux towers, which you might have heard of if you watched Ken Davis's talk. But I hope to convince you that these are not impossible to solve. And I'll show you a few examples, both from my lab as well as from some colleagues who have shared some slides with me later. And that tall tower eddy covariance in particular, which is in urban systems maybe the only way to reliably do eddy covariance, does require additional considerations for quality control. So I end my talk with some things that I need to think about and that you might want to think about as you're working with these types of systems. Okay. So I'll start with the Wikipedia-like entry of a eddy covariance and its basic principles. I think some of you are familiar, maybe at least in the basics, right? The idea here is that because the lower atmosphere, due to the friction of Earth's surface and the heating of Earth's surface, is always turbulent. There are always eddies that are mixing and swirling the atmosphere. And because of that, we can take advantage of that fact. And because of the way the laws of turbulent fluid mechanics works, measurements of that turbulence in terms of the mixing of that air and its covariance with changes in concentration or properties like temperature, moisture, or carbon dioxide, or methane, or others, allow us to infer the surface exchange if we solve that equation, the budget equation for the fluxes at the surface. And that's a pretty neat idea, and it's been around since the early part of the 20th century in theory, and since the middle part of the 20th century in terms of initial technology to actually make those measurements. And from about the 1980s onward, since we've had kind of more actual longer-term observatories that have been initiated through experiments, and then into the development of things like FluxNet and ICOS. The basic idea here is that although we can't kind of put an entire box over an ecosystem and just measure the inputs and outputs, if we put a tower in a turbulent fluid, then as air is moving past that tower and that air is turbulently mixed, then measuring at high frequency, the frequency at which the smallest eddies turn over, which is about tens to hundreds of milliseconds, along with a similar frequency measurement of water vapor or carbon dioxide or temperature, or preferably all three, we can estimate based on the essentially covariance of those two values what the surface flux is at in high frequency time steps, usually 30 minutes, which is enough to capture the range of eddies that occur in the atmosphere. You can think of the air as very much like a stream flipped on its side, right? So you get the same idea of looking at a river and seeing all those little turbulent and swirls in motion. Some of them are small, some are big, some are stuck on the side. In that case, in the river, the source of that turbulence is the gravitational potential of a river moving downstream. In this case, it's the same idea, except the source of this energy is coming from the large scale winds intersecting with the surface of the earth. So that's the basic idea. And it's not all that complicated, actually. The challenge is there are several big assumptions that go into using eddy covariance measurements on a tower. So one of those is that your turbulence is stationary. That means as the air is moving past the tower, its properties are not changing substantially except for the fluxes, the exchanges of gases and heat with the surface. Second, that as you're going across that surface, you're assuming in all directions that the wind is coming from, that the surface is essentially the same, that it's homogeneous. And that allows you to then attribute that surface flux to this type of forest or this type of ecosystem. And then this assumption has to be true for all wind directions too, because as we know, we can only sample where the air is coming from. And so hopefully in every direction that the wind is coming from, we have something that looks the same. So we need that turbulence to be stationary and homogeneous. And there's a few other assumptions that go into eddy covariance. We also have to assume that the measurements made at some height, the higher we are in the tower, the larger area we can see. That we call this idea the footprint. And so all of these things, but the higher we go up, the further away we are from the surface. And so some of the other terms in our turbulent flux equation that we typically ignore or assume to be small become more important. I'll show you at the end for tall towers, ignoring those terms is not possible. So here's another nice picture taken by one of our university communication staff of the tower. And no surprise, as much as we tend to think of our flux towers as located in homogeneous ecosystems, just from your eyes alone, you can tell that that is not the case. Clearly, there is a lot of heterogeneity across space as we look at even within a natural ecosystem. Here you can see grass and evergreen and deciduous trees. You can see some open areas that are wetlands. You can see a road even. And all of these things are going to contribute to that flux measurement. So there is no such thing as homogeneous. And as we scale out to even larger areas, so in this case, here's some air photos of places not too far from the tower, but maybe not quite in the eddy covariance footprint, there's quite a bit of signal of anthropogenic influence, right? So in this case, we see some forestry and harvest operations occurring maybe about 10 kilometers or so away from that tower. And to what extent do measurements like this influence, and how do we capture the influence of this if we're trying to scale up to some sort of biome or regional scale estimate? And probably to no surprise to anyone, this of course has large implications for using eddy covariance and using tall towers in urban systems. So this is a photo taken from an airplane by me by my phone, so very blurry, of Madison, Wisconsin, the city that I live in, that I'm currently in. And it's a nice wintry scene. We're a city wedged between two lakes, so we call our city, this part of the city, the Isthmus. And not surprisingly, if we wanted to think about where would we put a flux tower here, or where would we put a tall tower here, it's not very obvious to me. There is one tall tower here in the distance, but maybe that would not be ideal if what we wanted to do is understand, obviously, all these little smoke plumes here, many of these are power plants, how we could actually capture all of those dynamics. So I'm going to focus a little bit on natural ecosystems and come back to urban toward the middle of the talk, but I'll start with kind of what we've learned from doing work at our very tall tower site. And I want to acknowledge that I'm not the only one who's been working at this. The site has been established in 1995. And we've been looking at this system for a very long time across scientists, of course, even people before us. And I acknowledge the land that is belonged from time immemorial to the Ho-Chunk Nation and the tribes that have studied and looked at this landscape and has understood it as well as any scientist has. But even the scientists that have come before me over the last few decades, including at the National Oceanographic Atmospheric Administration, who helped establish the greenhouse gas tall tower measurements, some of the technicians and other scientists who have helped set this up as well. And I like this quote from Proust, right? The true journey of discovery is not seeing new landscapes, but in developing new eyes. And what I'm trying to do in our lab is to try to make eddy covariance have a different set of eyes than the way that we've understood this. And this isn't unique to this tower setting in this site. There's a recent paper by House and Chu at the Department of Energy AmeriFlux program showing that if we looked at these so-called footprints across many, many different ecosystems, and we said, these ecosystems, these towers all have target ecosystems they're trying to estimate the carbon flux from, for example. But if you look at the actual target area around a tower as a function of distance from tower and what percentage of the landscape is actually that ecosystem, you can see that it varies quite a bit and in some cases becomes very low. So here the dark colors show you how in the 200-meter radius, most of these towers have a pretty high representation of these ecosystems. But as you get further afield, you have less and less. So how do we deal with this? And so I'll kind of give you some examples. The first option would be, of course, to just ignore this problem and just make it go away and assume that if we make enough measurements, that the average will kind of average out. We could, of course, try to build more towers so that we capture all of this variability and maybe somehow combine it with tall tower measurements. Or we can try to do something different with space and time resolved fluxes, or using this idea that my colleague Stefan Metzger has pioneered of the environmental response functions. But there are some challenges we do need to consider. And then I'll wrap up with some final thoughts. Okay, so let's ignore it. Here are some garden gnomes doing a version of hear no evil, see no evil, speak no evil. So let's take a look at our tall tower again. So here's a map of the landscape and this box here is a 10 by 10 100 square kilometer region around the tower that roughly captures the maximum footprint that we see from this tower. And we've been making carbon flux measurements and heat and water flux measurements from this site. It's an AmeriFlux site, part of the program. And we have measurements at three heights, 30, 122, and 396 meters. And it is also a NOAA Tall Tower Program Greenhouse Gas Observatory, also known as LEF. And it is also a TCON site, so a total column observing network from Paul Wenberg's lab at Caltech. So they have a direct measurement of the entire troposphere column, CO2 and methane and other gas measurements. So I focused on the flux measurements first. And one of the things we learned is if we measure the annual net ecosystem exchange, this is the net carbon accumulation, where negative is a biospheric sink and a positive is a biospheric source, we see some very interesting patterns, right? We see a multi-decadal pattern where this site, the region as a whole, became a source. This was in the late 1990s. So you aligned this to American television shows to help engage my student audience, for example. So we call that the Seinfeld era. becomes a carbon sink sometime in the mid-2000s. You can almost say it's like a trend, and maybe this is because of higher CO2 and longer growing seasons, and so the era of the office. And we get into the era of Stranger Things, where all of a sudden that kind of increasing sink trend kind of goes away, and it becomes much more variable. So I kind of put this as a question mark. And we can't explain that with just any trends in gross primary productivity. So this is the photosynthesis component to that net carbon flux. There's not necessarily a trend. Some of the interannual variability is explained by this. So it opens this question of, well, can we explain this regional scale? This is roughly 10 kilometers upwind for the tallest height measurement of carbon uptake through some other towers. And the challenge is that when we look at complex regions, we have to ask, well, where exactly, what would we count as representative ecosystems from which to upscale? And if we looked at this in 3 different resolutions at roughly 30 meters, 1 kilometer, and 1 meter, 30 meters, and 1 kilometer, and you did some sort of basic land cover classification of the landscape, you would have very different opinions of what you think this land cover is. Where at the scale of, say, a satellite like MODIS, this whole area is just a mixed forest, which is my favorite land cover category because it basically sounds like we have no idea what is on the ground. It's just mixed. But it is interesting to think about, well, we know that it is roughly kind of 2/3 upland forest and about 1/3 wetland, right? If we kind of combine some of these, that seems reasonable. So maybe if we added some towers in a upland forest and a wetland, and maybe we could explain the variance in our fluxes. And the short answer to this, as you're probably not surprised, is no, we can't. So here I'm showing the NEE in a different format. It is a cumulative function here. So the black is now showing every year starting at January 1. It's kind of like a bank account. Where do we end up at the end of the year after we have our carbon going in and carbon going out? And so the black again is our tall tower. And here we added in 1999 a mature forest that looks like a lot of the nice intact mature forests in the region. And to no surprise, it is a very large carbon sink that seems to kind of do its own thing. It has some coherence with the tall tower, but it is a much larger sink. So it cannot explain what's going on. We looked at a wetland. So we set up a wetland in 2002 that's still running, even though my lab manager rolls his eyes every time he tries to keep this tower from sinking into the bog. But again, it is a medium-sized sink with very low interannual variability. We're discovering all the wetlands around this area really have virtually no interannual variability because it's this trade-off as the water table changes with climate between respiration, photosynthesis, and methane production. And we said, well, maybe if we look at some of these older forests, this is an area that was mostly clear-cut in the late 19th century, mostly to build Chicago. And what happened to all of these older forests that are coming back? And that is a smaller sink, but it's still a sink. So this doesn't explain anything. So of course we asked, well, what if we built a lot of towers? Maybe we're just missing some important hotspots or something like that. So in 2019, I worked with some colleagues, including Matthias Mauder, who's on the call today, to set up an experiment that we call the Cheesehead Study. It's an acronym that you can look up. It stands for something long that I regret coming up with such a long acronym. Cheesehead is our local term of affection for the fans of our Green Bay Packers football team because we produce a lot of cheese in this state. My former postdoc, Brian Butterworth, wrote this very nice paper in the Bulletin of the American Meteorological Society that kind of demonstrates what we were trying to do here by combining boundary layer observations of flux towers. We set up 19 flux towers, which is a little bit intense. Along with flux aircraft, we had 85 hours of flux aircraft measurements and hyperspectral observations and drones and weather balloons and everything else. Lots of fun. And you can see the heterogeneity in the ecosystem, everything from lakes to wetlands to some open fields. And the nice thing about kind of putting all these towers near our tall towers, the footprints almost somewhat overlap and they're very representative of the landscape. Well, so did we do any better? We're still trying to figure that out. And I'm going to switch gears from carbon to energy cycle, just because that's what this project is primarily focused on. But let's look at the middle panel here, which is called latent heat flux, which is another term for evapotranspiration. And you can see here the evapotranspiration flux in black from the tall tower And the span that we see from all of our 18 towers, other towers, is there's quite a bit of variance. And it doesn't really seem like the black is necessarily in the middle of these. We're working with the colleagues at Karlsruhe and Leipzig, and Louise Vonner, who is a graduate student with Matthias Mauder, supervised an undergraduate, Christine here, who did a very simple upscaling of those tower sites in the gray and tried to compare it to the tall tower evapotranspiration or latent heat flux. And you can see, yeah, we can do a little better, but it still doesn't explain all the dynamics, at least in a 3-day study. One of the things we've learned is that we can't easily randomly upscale in this system because there is a lot of small scale activity occurring across the landscape, in particular land management, which occurs in relatively small scales depending on where harvest is happening in sales. This is a harvest, for example, that happened near one of our flux towers that removed about 30% of the biomass. It's a lot of trees though. So we have been looking at a lot of other data that's been collected by other teams in a larger region and trying to make a story of how stand age, in this particular case, is the covariate we need to include if we want to properly upscale the carbon cycle. And you can see younger forests and managed forests have very different dynamics depending on how old they are and what type of management operations that's been done to the site. So a long time ago, back in my dissertation, I actually did a version of this, not with quite as rich a data set, but with a good number of towers. And we demonstrated that actually, if we did have a condition sampling on particularly forest management, we could do a reasonable job of estimating the regional net ecosystem exchange. You can see there's a slight low bias here. If you look at the tall tower X versus the upscaled but Y, and most of that is in the respiration term. And that's something that we're still working on. My AGU talk, if you are planning to attend virtually or in person, we'll go a little bit into more details of some of the sources of respiration that we're trying to identify. But for here, I want to talk a little bit about something different, which is that with tall towers, we have some other independent ways to estimate that regional flux. Because we might ask, well, how do we know that's actually right? So here's a very old picture. This is from a paper from Ken Davis, actually, showing from that tall tower site, we have measurements of CO2 concentration at multiple heights. And you can see over the nighttime, the buildup, the stable boundary layer, and the stratification of CO2, the very high concentrations near the surface that get well mixed during the day. And we have here a radar wind profiler showing the growth of the lower atmospheric boundary layer, the height of the lowest level of turbulent mixing, up to about 1 to 2 kilometers. And you can see the eddy covariance flux changing with that time. Well, it turns out we can take advantage of some of those pieces of information to have independent estimates of fluxes at regional scales. And this paper I published a few years after that other paper I just showed kind of shows how we can actually compare 4 different ways to estimate regional fluxes. So the black curve here is my upscaled multiple towers. Here I've kind of applied a model to kind of smooth the data together, but you can see this shows a pretty large upscaled flux compared to an ecosystem model that is only calibrated to the tall tower, which kind of shows that smaller flux. And we can kind of estimate kind of this difference. And we can compare that to 2 different ways that we can use tall tower concentration or mole fraction measurements. One of these is this equilibrium boundary layer approach that was pioneered by Alan Betts and Joe Barry and others and applied by Brent Helliker to this site. And the idea here is that if we have concentration measurements in a well-mixed boundary layer and we assume some sort of subsidence velocity over multiple days of frontal and synoptic mixing, the time rate of change of multi-day concentration multiplied by that subsidence velocity estimated by either the change in boundary layer depth with time or through reanalysis model grids is an estimate of the net exchange of CO2 with the boundary layer in the free atmosphere and therefore a regional flux. And that's what's shown in the dot in the squares here on the right. And the triangles here is a more traditional atmospheric inversion of multiple mole fraction measurements that's used in Carbon Tracker, which also includes the tall tower measurements. And you can see they actually agree very nicely, even though the squares are from a single tower alone in monthly uptake. And that actually kind of helps confirm that the tall tower is actually doing a good estimate of the regional flux. And it's really our upscaling sampling that's the problem. And so that was one thing we could discover with an approach like this. So I want to switch gears to talk about urban systems for a few minutes. Just to point out that there are things that we can do similarly in urban systems. So this is work from Will Drysdale at York University and Adam Bond, who's now working on greenhouse gas policy at the UK. And the idea here is here's an 180 meter tower, I believe, and they've been measuring NOx fluxes, which is a useful tracer for anthropogenic emissions, NOx, as we like to call it. And one of the things we can do is we can estimate NOx is something that we actually have inventory emissions. So in the UK, there's a national inventory emissions of NOx. And this is the ring road around London. And this is the footprint of the tower. And it very conveniently samples what the emissions inventory says is the hotspot. Not surprisingly, because that's the center of London. And so here we've kind of zoomed in, and here we've cut out that, here Will has cut out the emissions around the tower, sampling as if the wind was blowing from all the different directions that it actually did. So it's actually trying to do an apples to apples comparison. And we can actually compare it to what the tower said is the fluxes now separated by wind direction. So now we're looking at what each measurement is as a function of wind direction. And you can see there's some similarities, but there are also some subtle and pretty large differences in some cases. And we can use that spatial information to identify hotspots, which I won't get into, but it's something they're doing. But one of the really simple things you can do is identify by just scaling that up, your measured versus inventory emissions, that there's this factor of 2 difference between the inventory and the tower if you scale up with taking the footprint into account. And you can see if you do it by separate it by wind direction, you can also say that most of this bias is occurring from some source from the south of this tower. And this is a very unique way to use towers to better understand fluxes and better understand how things like reporting requirements for greenhouse gases, or in this case, an indicator pollutant, could be off, right? And this is something I think ICOS Cities is really well positioned to kind of do using the types of measurements they're making off of their towers. Now, something else you can do to kind of go to the next step is to really try to take advantage of that footprint information. And so work done by Stefan Metzger, along with my former PhD student, Ke Xu, is really trying to use something called environmental response function. Ideally, what we want to do is measure the fluxes around this entire box. And we wish we kind of had a giant box we could just stick over a city, like in one of those weird sci-fi movies where all of a sudden everyone is trapped inside a dome. But that's not what we're going to do because we like people. But we might say, well, a tower actually measures some box like this. And if you have multiple heights of measurements of concentration and fluxes, and hold on a second. Bye, Sarita, I love you, have a great day. Is that we can see fluxes from different locations at different times. So this is a nice cartoon that I kind of stole an idea from Happe Schmidt. This idea that, you know, as we sample from 1 hour to the next, we kind of are like a flashlight in the dark with our tower. And we can see different locations of the landscape in the same way that kind of people looking at an elephant from different angles can kind of describe an elephant in each of their own ways. But when you put all their ideas together, you get the whole elephant. And that is the basic idea of environmental response functions without going through all the ugly math. There's a lot of papers now out on this idea, but the basic idea is that if we took advantage of the fact that every minute to the next, we're sampling a different area, and we actually use Natasha Klun, who's on this call, we use her model to estimate what we're actually seeing at any one moment. And we use a wavelet type decomposition to calculate fluxes at a higher time frequency than 30 minutes. We get down to 5 minutes actually. And then we find covariates. So in this case, we have to find what covariates do we believe explain flux. And then we apply some sort of machine learning or really fancy regression to upscale. And in this case, we're showing how one tower versus multiple towers versus aircraft would allow us to better and better resolve the spatial and time resolved fluxes around the tower. And that's, we can kind of do this in a very simplified way. And this works because even in 1 hour, so here's an estimate of the flux for every minute for heating and water fluxes. And the colors here show you the average vegetation in the footprint in that 1 minute or that 5 minutes and how that's changed over the course of the hour. And as we go from a browner landscape to a greener landscape, we can actually see this spike in latent heat fluxes and this decrease in sensible heat fluxes. This is actual observations and this increase in CO2. And instead of doing a traditional 30-minute flux calculation and calling this a single number, why don't we take advantage of the fact that we're seeing different things over the course of an hour because of gusty winds? That's pretty cool. So that's what we do. And by taking advantage also of the fact that this tall tower site, that our nighttime footprints, as is true for most sites, are much larger and much more spatially heterogeneous than our daytime footprints, given the nature of turbulence in nighttime stable and daytime unstable conditions. We might be able to actually kind of paint by numbers using this approach the actual fluxes across space. So this is just an example of the type of output we get. I don't expect you to understand it, but this is kind of a partial dependence plot of, say, in this case, sensible heat flux against the covariance that we provided across space and time. So including at the tall tower, a very useful metric, the relative height of the measurement in the boundary layer. So if we have boundary layer depth measurements from centilometers or LIDARs, this is something that Manuel Helbig has recently published in Agricultural Forest Meteorology, this idea of co-locating boundary layer depth and boundary layer profile observations with tall towers is essential. And the fact that the flux tower is actually, over the course of the day, sampling different heights of the boundary layer, because the boundary layer height changes while the measurement height stays the same. We can actually retrieve the sensitivity of fluxes to a whole variety of variables. And with that machine learning, upscale those fluxes, in this case, sensible heat in the upper left, latent heat flux in the upper right, and CO2 flux in the bottom. And you can see a lot of interesting spatial variability. You can also say, hey, what are all those white spots? It looks like you didn't finish your painting. And these are not happy little clouds. These are actually where the machine learning algorithm is telling us we do not have the appropriate drivers to explain, or we do not have fluxes that have been measured in this combination of drivers to explain the flux. And therefore, the flux that's measured here is not representative of these regions, at least to the extent that we know. This is very useful because this allows us to say, for example, for this 1 hour, this measurement is representative of 60% of the landscape. So we can actually come up with a metric to identify for how every 1 hour is representative of any one measurement. And we could actually then apply that over time to do a quality control. We can also do things like, instead of looking at spatial variability, see what the distribution or histogram is of this flux measurement relative to what we measured. And we can see that in all cases, the distribution is broader, and in some cases shifted, so that the mean of the flux is different than the mean of the flux that we measure at the tower. And we can see in the case of CO2 at the bottom, we're missing some of these very large sinks, as well as these relatively large high flux hotspots that might be require targeted measurements that we otherwise would have kind of missed in our traditional flux calculation. And so one of our goals with this project is to really try to modularize and make this more applicable. Right now, this requires the 10 Hertz high frequency measurements and requires quite a bit of computational time to calculate. We have some proposals that we're hoping to write and support soon to kind of modularize this and allow this to work with lower frequency measurements. And we're hoping to apply it to a larger number of flux towers and possibly even to ICOS Cities towers. One of the things we can do with a system like this is we know that eddy covariance flux towers typically have this low bias in measuring the energy balance. That is, the sum of the turbulent fluxes does not add up to the total available energy. And this is a known issue with flux towers. And there's a number of hypotheses why, and Matthias Mauder in particular has been a pioneer of demonstrating how some of this is related to larger scale transport in the atmosphere. And one of the neat things that's encouraging is when you do apply this volume integration of the fluxes using this ERF approach, we actually do increase the turbulent fluxes in a way that's consistent with improving the energy balance. And so in many ways, energy balance can be a useful indicator and quality control indicator for your flux measurements, especially if you've applied some of these footprint weighting approaches. Finally, in the last couple of minutes, I want to talk about the idea of the tall towers. If you are going to use these in any site, including whether or not these are in urban systems, require some care and feeding. Here's a picture of one of our climbers showing in a site. Hopefully you're not getting too dizzy looking at this, looking down from our tower as they climb up on the ladder. I don't climb. I am a certified tower climber. I do not climb the very tall tower because that thing terrifies me. But it is an interesting system, and maintaining a tower like this is a lot of work. Being able to get up to these heights, being able to deal with icing and being stuck in cloud, and being able to identify when or you're not in the boundary layer and whether your measurement is appropriate for surface layer fluxes is hard. One of the things we know for sure with a tall tower is that profile measurements are essential. So here from a paper I published in 2015, where you're looking at methane flux measurements off of this tower, we show that on the top is just a concentration profile at 3 heights of methane and CO2. And you can see again that strong stable layer buildup of high concentration near the surface. That's the black line at 30 meters. And there's turbulent fluxes that can have very, very different patterns. And net ecosystem exchange, or the net surface flux, is both the turbulent flux, but for tall towers, you also have to include the net change of the so-called storage flux, or the change in profile vertically integrated with time. That is one of the terms that as many flux towers typically ignores. But for tall towers, you cannot, because in the night in particular, about 3/4 of the flux is actually in the storage flux, because we are above the boundary layer, therefore above turbulent mixing, and we essentially are running the tower like we've just put a box over the city. And it's the concentration profile and this buildup with time that is the most important information. And we, at least for this site, we need at least 3 heights of profile measurements to make a reasonable estimate of storage flux. We can apply the ERF method to the storage flux, and Ke Xu in her dissertation did that. And you can actually then come up with volume integrated concentration profiles using concentration footprint approaches. This is an advanced topic, but just to say, we can actually then improve our spatial time resolved estimates in net ecosystem exchange by combining the profile measurements with the turbulent flux measurements above it. Another thing we have to take into account is if you are sucking air down hundreds of meters, or even if you are not, just given the larger scale of eddies, the higher up you are in the atmosphere, you can kind of think of it, the eddies get squashed as you get closer and closer to the surface, means that you have a greater likelihood of high frequency spectral loss in your measurements of carbon dioxide and water. This paper from Brad Berger in 2001 particularly analyzed this for the tall tower, and spectral corrections are no joke. In a site like this. For a lot of small towers, it's usually just a few percent. In this tower, it can be like a 10% correction in the case of water, because water in particular sticks to tubes. Finally, just to point out, here's, for example, one of our very brave tower climbers bringing up our sonic anemometer assembly. We call them cowboys because of just the way they work and their very interesting demeanors. But just to keep in that, you do have to treat your staff well, and you do have to think a lot about real-time monitoring and identifying problems and identifying better quality control for, like, when does a cloud come through your site and cover your sonic anemometer of ice, and how long does that ice take to melt? These things are kind of the headaches that keep me up every day, but things to keep in mind with tower sites. As they get taller, they become more difficult to maintain. Finally, I'll just say we do have a special issue on scaling of land-atmosphere interactions. This is a cross-AGU journal, including JGR Biogeosciences, on which I'm editor, JGR Atmospheres, the Journal of Advances in Modeling, and Earth and Space Science. And we just extended the deadline to May. So if you have some interesting ideas and you'd like to publish, I should also point out for AGU with Project Deal, we have gold open access with no page charges for a large number of German institutions, as well as some other institutions across Europe. So you can publish in here, open access. And so please take a look. We have some great papers coming out, advancing some of the topics even I just presented today, already published. So I think I've roughly got you within 30 minutes, maybe a few minutes late, so I apologize for that. But you have my email, website address, and my Twitter handle if you want to find me or see the silly or stupid things I say in social media. And I currently encourage my collaborators, Arlen Andrews at NOAA, Stefan Metzger, Ke Xu, Ken Davis, Brian Butterworth, all of the folks involved in our so-called Schwamigan Ecosystem Atmosphere Study team, or the Cheese team, the Cheesehead 19 study, and the nearly 40 plus investigators in the field who helped make those measurements, and Will and Adam who provided the information about NOx. This work has been supported by the National Science Foundation, Department of Energy, USDA, NOAA, and NASA. And so USDA is agriculture. And here's another nice picture of an autumn scene. This is September. This landscape is getting snow covered as we speak. So we're getting ready to winterize everything right now. So thank you.
Fantastic. Thank you very much, Ankur. That was a brilliant talk. And I am sure that we have questions. Well, I see applauding emojis in the participants. Yes, there is from Andreas. Would you like to just ask your question? That might be easier.
Okay.
I can also ask it in person. So thank you first for the nice talk. You showed the importance of the storage correction on tall towers. And so I'm really wondering how we should deal with this in a city, because if we have a tower at one location and we measure a profile down, we talked about this last week in the kickoff meeting, this might not be representative for the actual storage change of the entire volume that affects your footprint. And I'm not sure how we should deal with this. Have you thought about this, or have you similar experiences with heterogeneous ecosystems?
That's a good question, right? So the question here is, if we're measuring concentration at multiple heights and we want to estimate storage flux, which is the integral of those measurements with time, how do you actually know that those measurements are representative of the same source area as your flux measurement? And that is certainly something we've thought a lot about. Yeah, as you know, our current practice is to ignore it and to assume, and I think for the upper heights, that's a reasonable assumption, because in a well-mixed boundary layer, concentration profiles should not be changing all that much across space. And even in a stable boundary layer, that's likely the case. So certainly the lower height measurements, that's something that may be not true. There's a couple of things we thought. I kind of briefly hinted at it at the slide that I went through very quickly, which is that you can apply something like the environmental response function method to the concentration if you use, instead of a flux footprint, a concentration footprint, and then try to re-upscale that concentration measurement across space and then calculate storage flux for every grid cell. What we found when we did that, at least for our tall tower site, was that it didn't make that much of a difference. Like, it allowed us to get some more spatial. Most part, it was pretty small. And, oh, sorry about that. And so that's an interesting point. I think for an urban system, it's going to either require doing some sort of pilot studies where you're making multiple concentration measurements and somehow scaling that, or doing some sort of probabilistic estimate for that storage flux to kind of integrate some of the uncertainty you might have, especially at the lower level concentration measurements.
Yeah, thank you.
Yeah. Let's see, another question came in the chat from Dominic.
Yeah. Hi, may I ask this question?
Yes, go for it.
So I'm especially interested in nighttime fluxes, which are, well, turbulence is less active, and you have these storage terms. So I think you mentioned that you measure fluxes at different altitudes on the tower. So you can evaluate those fluxes and see whether they are consistent with the storage that you derive from concentration profiles. Is that something you have tried, and to check whether these, especially the nighttime fluxes can be trusted?
Broadly, so the question of we do measure turbulent fluxes at multiple heights, at 3 heights in this tower. And the question is, could we do some sort of consistency check between the storage accumulation flux and the turbulent flux over some time period? The short answer is we have done some level of tests that make us confident that, for example, our lower level turbulent flux measurements are consistent with the storage flux over time. So the 30-meter level, for example, is almost always in the boundary layer, and those fluxes seem to kind of follow and link with the storage profile across the entire tall tower. There's a little bit of a catch to that, though, which is that the 3 heights measure different footprints, and so we don't have an exact way to do this. So the 30-meter level tends to sample some of that clearing around the tower at a greater fraction, on the order of up to 10 to 20% of the footprint, sometimes even 50% depending on the conditions. And we know that that grassy clearing has a very different flux profile. I think certainly higher respiration, especially when the person who runs the tower likes to drive a snowmobile around in circles around the tower. So there's we can't necessarily do that calculation well. The thing that does help us, though, is that as you get above the surface layer, the first 50 meters or so of the atmosphere, your flux footprint, the area that you sample upwind doesn't change as quickly with height in the convective boundary layer. There was a nice paper by Wigwell Wang that showed how you can come up with convective layer footprints. And our 120 meter level and our 400 meter level footprints are actually surprisingly very similar. So at least for the upper heights, we have some more confidence that we can kind of combine those two measurements. And that's exactly what we do when we produce because of course for Ameriflux and FluxNet and even ICOS, you need to provide a single number for a flux, for an NEE. And so what we do is we take the highest height we can in the daytime, or we combine the upper two heights if there's some quality control issues. And then at night, we take either the middle level if the sensible heat fluxes are positive, or the lower level if the sensible heat fluxes are negative. We are mixing, and we have some footprint issues with that. And there's, of course, a lot of caveats if you're using the tall tower data in the way that you would traditionally use smaller tower data and kind of synthesis and flux upscaling and things like that. You really can't use this tower data in the same way.
Thanks.
Okay.
At the moment, I don't see any raised hands or other questions coming in. And if I miss somebody, then please just do speak up. There we go. Do you consider adding, well, you can read by yourself.
Yeah, Cintilometry.
Go ahead.
Yeah, this is something, I talked to Matthias about this. I know there have been some studies in Europe where they've done scintillometry. For those who are not familiar, scintillometry is this idea of using the changes in refraction of light due to turbulence. So if you've ever looked at a really hot day or an oasis in a desert, you kind of see the air all kind of refracting and kind of looking weird, sometimes causing false images on the ground, mirages. You could actually measure that change in light refraction across two different detector and receiver and estimate turbulent heat fluxes and then other fluxes across large distances on the scale of kilometers. Very cool technology. Is very, very hard to implement at this site because all of the trees are pretty tall. So you would have to have two very tall tower sites that could get above the landscape. And so we haven't tried it here. It'd be very interesting to think about it. I have seen some of the studies that showed some consistency in doing scaling with that. What we did do in the Cheesehead study was we used a flux aircraft. So you can do eddy covariance on an airplane. Flying at low altitude. And in fact, the London study also did something like that. They have a paper recently published where they applied the ERF technique to their airborne studies. That's Adam's work. And the nice thing about that is you can do spatial eddy covariance and you can look at leg average fluxes and you can split those up with time. And a PhD student in my lab, Srinath Valeri, is about to submit a paper on that. And we can kind of compare that to our despatialization from our single tower. And that's kind of what we're hoping to do soon. And then there's another question from Andreas. Hi. Thanks for widening perspective of eddy covariance and landscape. You were mentioning that flux measurements needed to be in the atmospheric boundary layers, or specifically in the constant flux layer. Textbooks tell us this is the lower 10 to 15. How do you make sure you're measuring in that layer? Yeah, so this goes back to this point of our flux measurements, right? The theory of eddy covariance assumes that the flux that you're measuring at some height is representative of the surface flux, and that works in the surface layer because the scaled fluxes with height should be constant. So we also find, or a small variation. So it's called the constant flux layer. And that's part of the reason you can get away with not having to measure storage fluxes at a lot of tower sites, for example. This is a big puzzle for us. How do you actually measure? So the problem is when you get to higher heights, you do have this an additional term called the vertical flux divergence, right? The idea that fluxes are linearly decreasing with height. The short answer is, I don't know. I'd love to get a solution to this. What we typically do here is, again, use this algorithm that was published in the 2001 paper to select a height based on the sign of the lower level heat flux to say, are we in a well-mixed convective boundary layer or not? If we are, we do know that the storage flux is an important term we can't ignore. And that seems to, for the most part, do a good enough job of estimating regional flux and getting us a turbulent flux. We can see at night, like if you look at the 400 meter level eddy covariance data, that vertical velocity is doing nothing. You are clearly in free atmosphere above the boundary layer. And you really are relying on concentration profile to tell us what that nighttime flux is. And the turbulent flux is really adding very little information. But in the daytime, it is clearly turbulent, it is clearly resolving large eddies, and it is clearly similar fluxes at the heights that we see, especially when the footprints overlap. And so that gives me confidence that that vertical flux divergence term is probably not a major player, at least in the way we're calculating fluxes. But I could be wrong. And we've had many of debates about this. And it is, again, one of the reasons that these types of tall towers do require additional thinking. And the nice thing with the ERF approach is we can kind of get away from those assumptions by essentially just combining all those levels, boundary layer depth measurements, and the concentration profiles together to kind of come up with some sort of volume integral, solving for as many of the turbulent flux budget terms as we can using the same approach. And that's kind of where we want to get to with that measurement method.
Yes, okay, thank you very much. We are starting if I may, just hi. We are starting tall tower measurements now here in Denmark. And we have already some experiences at the research tower. But that is an open question. We can measure the boundary layer height, but the constant flux layer height is difficult to estimate. And that's a good idea to look at different criteria, but they will be soft. It's not easy to really say, now that's the right flux. And probably having two height measurements at the same time could, of course, solve a little bit of problem. Also flux measurements, not only concentration measurements.
Yes, it's having multiple flux measurements, even though that adds a lot of cost and data processing, has been essential for us to kind of feel that we can trust the measurements we're making on this site.
One can, we are trying to, we will establish an array of 3 sonic nanometers, so you can decide maybe from the sonic data whether you're on the right flux, and then the scalar can be measured at that height where you assume that's the highest level that is still valid for flux measurements.
Interesting. Yeah, we should follow up on some of your ideas, because I'd love to test some things. We have 25 years of data from this site, all the way back to when the data was stored on tape drives and everything else. And so it'd be fun to kind of reapply some different quality control criteria to some of the to the longer term data sets.
Yeah, okay, good, thanks.
Well, thanks everybody, and especially to you, Ankur, for this really interesting talk and this nice discussion we had. We are just on time to finish, I guess. Yeah, there is no more questions coming in. So again, thank you very much. And to everybody, I would like to remind that we have another talk next week, which is tackling the whole, well, not problem or the challenge, I would say, of measuring greenhouse gases from a different angle, which is the attitude towards climate change from people and more a social aspect from the citizens. So I am really looking forward to more